Welcome to University Physics. I know that reading a science textbook can be hard work, but it is so important for this class that I'm recording these short introductory videos for you to preview your chapter so you can dive right in. We begin by learning to describe the motion of a simple object quantitatively, that is, using numbers, by constructing a motion diagram. A motion diagram is like strobe photography of the motion of an object over regular intervals of time. Can you see from this motion diagram where the ball is moving with a larger speed, with a faster speed? Well, let's compare. From this initial time to that final time, the ball has traveled a distance d. And if we divide that distance d by the time interval between this position and that position, we will get the speed during that interval. Whereas at a different place, say from here to here, the ball has traveled a smaller distance. If we divide that distance by the time interval delta t, we get the speed. Comparing this speed to that speed, we can see that the ball is moving slower. The ball has less speed at this position. At the top, of course, the ball has even less speed. It's kind of blurred together, but from one moment to the next, it might only move just. A motion diagram can be used in elite sports coaching as well to describe complicated motion in 2 or 3 dimensions. As this golfer swings the club, can you see where the club is moving the fastest, the slowest? Comparing these 2 points right here, during this time interval, the club only travels a small distance d, so dividing that by the time interval delta t will give me the speed at this over this time interval. Whereas if we were to find another place, say down here, the club travels over the same time interval a larger distance. The distance from initial to final is displacement in this direction. That displacement, or distance, divided by the time interval is the speed at that location. We can compare the speed here to see where the club is moving faster. Another place the club seems to be moving fast is from this position to that position. We also see other interesting things. Here the club dips down and then comes back up. That gets interesting. Another thing that's interesting to note is look at the speed before the club contacts the ball and then the interval that includes the contact with the ball. That is a smaller displacement. Why? Did the club slow down because of the ball? Well, this is a good time to talk about the point-particle approximation. Now, modeling, a principle in modeling is that everything should be as simple as possible, but not simpler. Along this club's motion, we can consider the club to be something that doesn't have a shape that's changing. The shape doesn't really matter. As far as we are concerned, the club is simply a dot at the end of a stick, and the stick is not bending. That's a pretty good approximation for most of this motion, except maybe for this dip. Something interesting is happening there. The club is bending, so the club head comes in closer. The point-particle approximation breaks down here, but it's pretty good for the rest of it. Now, I don't think the club is slowing down here per se, so much as the club head hasn't traveled as far. Now the club itself has probably flexed a little bit. We can't see that very well. The point-particle approximation is too simple to understand the dynamics. Just wanted to point that out because you will read about the point-particle approximation. This fellow has the curious habit of riding for an hour at a time, going nowhere in particular. I tracked the motion of his ankle and his knee. Interesting things could be done, for instance, looking at the flexion of the ankle throughout the motion, but I'm just going to track those 2 points in the tracker software. You see the red dots. So at various times I've outputted the x and y coordinates here into a spreadsheet, and I've made a graph. What kind of graph is this? Is it a function? Well, no, I remember from Algebra 2 that in a function, every position on the horizontal axis can only have one value on the vertical axis, but there are two values here associated with the same place, so this is not a function. The rest of the story is each of these places is a parametric function in time, but y is not a function of x. We can tell the same story with the graph of the vertical position of the ankle as a function of time, and we can see that is sinusoidal motion. Circular motion is generally sinusoidal motion if we look at one coordinate as a function of time. Notice this is time and this is position. Let's work an example. Now your book is full of many examples because we can learn from examples. And I encourage you to do that. Learn from the examples in your book so that when it comes time to do the homework, you can do that homework independently. Jenny runs 1 mile to the northeast, 1 mile, and then 1 mile south. Graphically, find her net displacement. Now, displacement does not mean how far did she run. It means what is the difference between her final location and her initial location. The displacement can be represented as a vector that goes from initial to final. That would be her displacement. And if we were to also ask what is the value of her displacement, and even what is the angle of her displacement, you could do that too. You would do a little bit of trigonometry. I would break this triangle up into right triangles because I know a lot about right triangles. If I knew the length of this side, let's just call that A, and this side, oh, let's call it B, then this side would be the square root of A squared plus B squared. That would be my solution strategy. That would be her displacement, the magnitude of her displacement. But since we're talking about this, let's do a quick trig review here. If this angle here is known, and it is known to be 45 degrees, then this side is the adjacent side to that angle because this side is touching the angle. This side is the opposite of that angle, it's not touching. This side is called the hypotenuse. And so, what I remember from trigonometry class is that the tangent of the angle is equal to opposite over hypotenuse. And the sine of the angle is equal to opposite over hypotenuse. Oops, I made a mistake there. Did you catch it? The tangent of the angle is opposite over adjacent. And the cosine of the angle is adjacent over hypotenuse. So what if I want to know that adjacent side? I want to know the adjacent side. I know the hypotenuse side is 1 mile. I know the cosine of theta is, well, cosine of 45 degrees. Could I calculate the adjacent side? Well, I need to get it alone, so I'm going to multiply both sides by h. So these h's cancel, and the adjacent side is equal to the hypotenuse times the cosine of theta. In other words, the adjacent side is equal to the hypotenuse, 1 mile, times the cosine of 45 degrees. And when I multiply that out, I get 0.707 miles. So that is the length of this adjacent side. What about the opposite side? Well, you can follow the same sort of logic, and you would find that the opposite side is equal to 1 mile times the sine of 45 degrees, which, multiplying that out, you would also get 0.707 miles. This is a special triangle because that's 45 degrees. So what is B then? If this length is 0.707 miles, this extra bit of length must be whatever we need to get up to 1 mile. So I'm sketching out a strategy here. I started with the end in mind here. I want to get the displacement, and I need to know B, and I need to know A. And I'm starting to work out, well, how do I get A? Here it is. How do I get B? Well, I think it comes from this opposite side and the fact that the opposite side plus this extra little bit is equal to 1 mile. So now I put the pieces together and solve. B, therefore, is equal to 1 mile minus the opposite side. The opposite side is 0.707, so B is equal to 0.293 miles. So I have a triangle here, this triangle here. I'll draw it again. It has a side A and a side B, which is 0.293 miles. A is 0.707 miles, and therefore this hypotenuse is the square root of that squared plus that squared. And when I multiply that out, I get the displacement is equal to 0.765 miles. Now let's evaluate. Does this even make sense? Well, 0.765 miles is less than 1 mile, so that seems reasonable. This can't be more than 1 mile. That wouldn't make sense. So I would say, yeah, that's within the realm of reason. If I was to draw this more carefully, I think I would be able to compare my numerical solution to my graphical solution. So there you have it. That's one example. Your book is full of many examples. Take a little time to review those examples, glean what you can, so your homework will go quicker. It's like what Benjamin Franklin said, a stitch in time saves 9. You don't have time to not review those examples if you're getting stuck on your homework. Okay, post whatever questions you have in your reading, and we will pick up this discussion in class. I'll look forward to seeing you then.